Hello and welcome. In this video, I'm going to be showing you how to find the absolute maximum and absolute minimum of any function. Not all functions have an absolute maximum or absolute minimum, but if they do, this video will show you how to find them. All right, let's first of all start with the definition. An absolute maximum is a y value that is bigger than any other possible y value for the function, the literal maximum y value of anything. And likewise, the absolute minimum is the smallest, the lowest possible y value. So let me show you a visual real quick. Here's a function that I've used before in chapter 4, this W looking thing. We found things called local minimums and local maximums. This right here is a local maximum. In this region, it is the highest y value. Everything to the left, everything to the right is lower. So that's a local maximum. There's a couple local minimums over here and here. This local maximum is not the absolute maximum because the y value here, the highest y value here at this local maximum, is not the highest y value overall. There are much higher y values over here. There's a y value of 37. At the local maximum, the y value is 0. However, right down here, the local minimum, there's two of them, two local minimums. The y value is negative 64, and nowhere on this function is there a y value that's smaller than, that's lower than negative 64. So this particular local minimum also has an absolute minimum of negative 64. So that's what we mean by absolute maximum, absolute minimum. All right. So the thing about an absolute max and absolute min is that they are always going to occur either at a critical point, which we've found several times before, or at an endpoint. So these occur, these always occur at either a critical point or an endpoint. Now, most functions don't have natural endpoints. Some of them do, square roots and logs and stuff like that, but most of them, we're going to just force some endpoints. So you can look at example A right now. You can see I have a function here, and I just threw a couple endpoints in there. So the domain says that x is only allowed to be between negative 30 and 100. So these are now endpoints. Negative 30 is the left-hand endpoint, and 100 is the right-hand endpoint. And so I know for sure that if there's an absolute max or an absolute min, they're either going to occur at a critical point of the function or at one of these two endpoints. Now, I'm going to show you now how to follow the steps and determine the absolute max, absolute min if they do occur. One thing back at this function, I think I forgot to mention, there is no absolute maximum because the function keeps going up and up and up and up forever. So we don't have infinity as a maximum value. It's going to be a y value. If it exists, is an absolute max, and there is no y value, which is the absolute max. It just keeps going up and up. So this graph has a local minimum at negative 64. Notice it's a y value, and there is no absolute maximum. And I guess I'll say that one really briefly too. Up until this point in chapter 4, when we look for things, we're looking for the x value, the critical point basically is an x value, inflection point is an x value. The absolute maximum, absolute minimum are y values. So try not to be one of those students who's tricked when they're typing in one of their answers and you're asked to find the absolute maximum and you write down the x value, it'll be marked wrong. You have to write down the y value. All right, well, we'll do a few examples and you'll get the habit of how it works. All right, so I have this function here in example A. I'm going to find the critical points. I'm going to find the endpoints. These are all the endpoints. And of those critical points and endpoints, I know if it exists, my my absolute max and absolute min are at one of those locations. All right, so we've found critical points many times before. In fact, I think I've found critical points of this function, But let's just do it again to make sure we got it. So critical points happen when the derivative is equal to 0 or when it's undefined. So I'll just find the derivative here using my calculus shortcut rules. I'll have the derivative equaling 0. And I also need to figure out when the derivative is undefined. Those are called critical points. Okay, well, do some algebra here. Divide by 4. In fact, what I'll do is I'll write the negative exponent as a 1 over. And divide by 4. So negative exponents mean reciprocal, and I divide both sides by 4. I've solved this a couple times before. One time I cleared the denominator, and another time I just raised it to the negative 3/2 power. I'll show you another way of solving this equation. Again, if I apply the same thing to both sides, it's still an equation. I'm going to flip both sides. So I'm going to flip the left-hand side. That'll be x to the 2/3 over 1. And I'm going to flip the other side, which is 4 to the 4 over 1. So these are over 1. But over 1 doesn't do anything. So I can flip one side, flip the other side, and do the same thing to both sides. And we're good to go. And so from here, we get x to the 2/3, and I raise it to the 3/2 power. And that just gives me x. And 4 3/2 power is the square root of 4 cubed, which is 8. So x equals 8 is one of our critical points. And then we need to find out when the function is undefined. So that's supposed to be negative, it kind of disappeared. So undefined is when the function can't be calculated. So things that are undefined would be like division by 0. We can't divide by 0 and calculate anything. We can't take a square negative number and calculate anything, well, nothing real at least. You can't take the log of a negative number, or you can't take a log of 0. You can't take the tangent of pi over 2. There's a short list of things we can't do. In this particular one, we do have a possibility of being undefined by dividing by 0. And that's because a negative exponent is just a code for, a reciprocal for division. So this is really 4 over x to the 2/3 equaling, or minus 1, sorry. And is this undefined? Yes, it is undefined. So yes, when x equals 0, it's undefined because you divide by 0. Not allowed to divide by 0. You can try to divide by 0, just there's no answer. So x equals 0 is another critical point because it is where the first derivative is undefined. So we have two critical points, x equals 0, x equals 8. Both of them are legal. They have to be in the domain. Remember, we're only considering x values between negative 30 and 100. X equals 8 is between negative 30 and 100. X equals 0 is between negative 30 and 100. So those two critical points, they could be absolute max, absolute min. All right, so first step, find the critical points. We found them. Second step, we found the endpoints. Well, they're right here, negative 30 and 100. Those are the endpoints. And the last step is just figure out which of them is absolute max, which is the absolute min. So I'll make a little table. Remember that the absolute max, absolute min always occur at a critical point or an endpoint. Well, what are our critical points? 8 and 0. What are our endpoints? Negative 30 and 100. So that's the list. That's it. If we have an absolute max, absolute min, it's got to be one of those four places. We need to find the y value because the highest y value would be the absolute max, and the lowest y value would be the absolute min. So we got to find y values. So let me write down my y function again. I'll just use Desmos and make a table out of it. So the y value is 12x to the 1/3 minus x. And I'm going to plug in those four values. So let me go to my calculator, find the function I want, which is right here, 12x to the 1/3 minus x. And I'll just make a little table out of that guy. And once again, just to remind you, 8, 0, negative 30, and 100. So 8, 0, negative 30, and 100 are my four. Let's get rid of this last one. Those are my four possible absolute max, absolute min. We know it occurs at critical point or endpoint, and there's only four of them, and there they are. So the y value here is 16. The y value here is 0, et cetera, et cetera. So what is the largest possible y value? It's 16. 16 is bigger than 0, bigger than negative 7, bigger than 44. So the absolute maximum is 16. So right here, we have 16, 0, negative 7 point something. I'm not sure how to do this. Negative 7.28 and negative 44.3. So 28, blah, 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 negative 44.3, blah, 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 blah. So this is the largest y value. So y equals 16 is the absolute max. And then we have this negative guy right here. Y equals approximately a negative 44.3 is the absolute min. And you may need to find the exact value of the absolute min. And we can do that just by plugging into the function. We know it occurs when x equals 100. So I take the y value when x equals 100. That means I do 12 times the x value to the 1/3 minus the x value. So this thing right here, we can't really get a whole number out of it, right? Because we know it comes out to be some weird decimal. So that right there, 2 times 100 to the 2/3 minus 100 is the exact value of the absolute minimum. If you want to know the exact value, the approximate value is negative 44.3. Okay, that's how we do absolute max, absolute min. Just to go over that step by step again, find the critical points, find the endpoints, write them out, find the y value. Whichever y value is the biggest, we call that the absolute max. Whatever y value is the smallest, we call that the absolute min. Okay, let's just do some more examples. This video is going to be a little bit longer because I'm going to be reviewing critical points, inflection points, all the kind of stuff we've been doing up to this point, in addition to just giving some more practice on absolute max, absolute min. So we'll do a couple more absolute max, absolute min, and I'll start mixing in some of the previous stuff just to help you review some of the previous learning points in these 4.1 through 4.3 lecture notes. Okie doke. Example B. And as always, I'll just remind you, as I sometimes forget to do, but as I just remembered, definitely feel free to pause the video and try things, right? Try things, see if you got it, right? I mean, right now, if you know the routine, find the critical points, find the endpoints, write them out. Whichever is the biggest is the absolute max, whichever the smallest absolute min. If you got that, try it, give it a go, see if you can figure it out. If you can, awesome. If you can't, you'll know where you get stuck, and I'll be able to help you get unstuck. So when it comes to do a test, you're like, oh, I got this down. All right. So if you are now returning, great. If you're just hanging out and watching me, that's also great. Let's do this problem where we're looking for the absolute max, absolute min. It does give us a forced domain, negative 10 to 10. This is pretty common with absolute max, absolute min problems where they just give you some endpoints because not a lot of functions have natural endpoints. So in that case, they oftentimes wouldn't have an absolute max, absolute min because it just trails off to infinity or something. So let's work on the critical points. That's finding the derivative. The derivative of this guy is 3x squared minus 18x minus 21. And I want to find out when that's equal to 0 and when it's undefined. You may now realize that in this case, it is never undefined because it's just a parabola. We don't divide by 0. We don't do any funky square roots of negatives or logs. There's no logs in here. There's no square roots in here. We can't do any of that stuff. There's no division in here. We can't do that either. So we will never have it undefined. But it is possible that we could have it 0. Let's find out by doing some simplification by factoring. You may recognize this problem. I've reused this equation a few times just because it's nice to illustrate several different things. So here I have x equals 7. That's a critical point at x equals -1. Those are both values of x that make the derivative equal to 0, and it's never undefined. So we have two critical points. Are they both in our interval? Yes, they're both legal because only x values between -10 and 10 are legal. So we got 7, we got -1. Those are the critical points. We also need the endpoints. Well, the endpoints are given to us, right? That's just where the function starts and stops. It starts at -10, stops at +10. So those are my 4 values that are possible absolute max, absolute min. And how do I determine? Well, I find the y value for each, and then whichever is the highest is the absolute max, etc. And once again, I'll just use Desmos to help me do the number crunching. So I need to find the x cubed minus 9x squared minus 21x plus 5 function and make a table for these values. All right. So where is that function? Is that one right there? X cubed minus 9x squared plus or minus 21x. Yep, that's the one. Right up here. And I already made a table from before in a previous lecture. So I'll just reuse this table, but I got to plug in the critical points and I got to plug in the endpoints. I'm guessing those are the critical points that I plugged in. Let me double check. Yeah, 7 and -1. Negative, okay, they're opposite, but you know, it's the same two numbers, 7 and -1 here. And I need to plug in the two endpoints. So the two endpoints, if you want to remember, are 10 and -10. I will show you that in a moment just to make sure that you see that. They were given -10 and +10. Those are our two endpoints. So if I make my little table here, let's see. Okay, I put it in the wrong table. Okay, sorry about that. Here's the table. So let's put into my actual function 10 and -10. There we go. Oops. -10. So for the function we're actually doing this problem, x cubed minus 10x squared minus 21x plus 5, these are the two critical numbers right here, -1 and 7, and these are the two endpoint numbers, 10 and -10. And so we look at here, what is the largest possible value? It's 16. And what is the most negative value? What's the lowest value? It's -1685. So that's our absolute max and absolute min. And so you'd have to show the table. I'm not sure how much time we want to spend with me recreating tables and stuff here. But on your homework page, 7 has the value of -240. -1 has a value of 16. -10 has a value of -1685. And +10 has a value of -105. So like on a test or something, you'd have to show me the table. You can't just say, well, I looked on my calculator and got the answer. You'd have to recreate this. And then you could say, oh, there we go. Y equals 16 is the absolute max. And right here, y equals -1685 is the absolute minimum. All right, if we look at this function right here on Desmos, that's this one here. Okay, so there's the function. It does go up forever. If I scroll out, it goes up and up forever. It goes down and down forever. However, remember, for this particular function, we have endpoints. We're only going from -10 to 10. We're only allowed to have x values between -10 and 10. So in Desmos, I can take a function and I can put in brackets afterwards. Not that kind of bracket, this kind of bracket. -10 and 10. Close bracket. So now when I scroll out, yeah, when I scroll out, I guess I have to scroll a lot here. I need to change the window settings because I can't see anything anymore. So when I just zoom in and zoom out, it does everything proportionally, and that's just going to be ridiculous. So the x values only need to go between -10 and 10. They don't need to go between -800 and or -600 and +800. So let me just go change that a little bit. X goes from, well, we'll do it like negative 15 to 15 just to give it a little breathing space so it's not like smushed against the edge. So there's negative 15 to 15 in the X direction. So that's the function now. And you can see that, of this function, the absolute maximum is somewhere right around here. And that's actually where X equals -1 and Y, which is the absolute maximum, is 16. And in this sort of, function where we have endpoints, right here would be the absolute minimum at an endpoint, and that's at -10 and -1685. So those correspond to what we found in the table. But you can visually see when we kind of chop off the ends and give it some endpoints, you can see where the absolute max and absolute min is. Okay. Again, I'm not going to do anything different for the rest of this video, except more examples and throwing in some more review. So we're just kind of practicing absolute max, absolute min, critical points, inflection points, etc. For this video. At the end of this video, I will, or at the end of the lecture notes for this section, I will have a bunch of vocabulary. So just be aware that there's a lot of vocabulary in this problem. I kind of summarize them on page 10. So you can check that out when you want. Okay. Next example I have here is example C. And I have this fourth degree polynomial here. I have a force domain of -10 to 10. And I'm looking for local max, local min, inflection points, absolute max, absolute min. So I'm looking for all kinds of important stuff. All right. So how do we find local max, local min, inflection points? Those are from critical points and from additional inflection points from the second derivative. How do we find absolute max, absolute min? Well, we find inflection points and we find endpoints. So we're going to do all that in one problem. All right, so a lot of it comes to finding critical points, which is the first derivative. So let me start there. So the derivative of x to the fourth over 4 is going to be x cubed. Derivative of -24x squared is -48x. And the derivative of plus 20 is plus 0. So I'm going to not write that at all. All right, so we need to find out critical points. This is never undefined because it's just a regular polynomial. So we don't have to worry about the undefined pieces of critical points, but we do need to make it equal to 0. And this one I'll factor as well. I don't want to give people the illusion that everything can be factored. Actually, a few things can be factored, but I set these up to be factored so that we could focus more on the calculus and less on the algebra. But be aware that not everything is factorable. We can simplify this by factoring as the difference of two squares, or you can solve using the quadratic formula, or you can just set it equal to 0. Let me set it equal to 0. Let me do it that way, just so I do something different for folks. We get the first thing equaling 0, or the second thing equaling 0. So here, x equals 0, that's a critical point. Boom. And then for the second guy, I'll just move the 48 over by adding. I'll take a square root. The square root of x squared is called the absolute value of x. Remember that, it's not x. Square root of 48 is some decimal. 7 times 7 is 49, so it's slightly less than 7, like 6.9 or something like that, 6.8. I don't know what it is, but it's some number. Instead of writing absolute value, a lot of people will write a plus or minus. So actually, it's over here, plus or minus. But there's no difference for writing plus or minus on the right side or the left side. So instead of writing it over here, most people write it over here. But that's why there's a plus or minus. It's because of the absolute value. So we get two critical points from the derivative equaling 0, or no, 3 of them. We had x equals 0 is one of them. We got x equals the positive square root of 48. That's another one. And x equals negative square root of 48. That's a third one. So we have 3 critical points. All right, next we're going to take the second derivative. So d2y dx2. So the derivative of x cubed is 3x squared. Derivative of negative 48x is minus 48. Okay, the first thing I do is I'm going to classify these guys as local max or local min using the second derivative test. So in a previous video, we talked about the second derivative test. So the second derivative test, I take each of the critical values, which are 0, positive square root 48, negative square root 48, and I put them into the second derivative. So the second derivative will tell me concavity, and depending on the concavity, I can classify them as local max, local min, or unknown. So we get 3x squared minus 48. All right, so I plug in 0. Remember, this is the equation I'm plugging into right there. I plug in 0, I get 3 times 0 squared minus 48, which is negative 48, which is less than 0. So the concavity is down. So what kind of critical point has a downward concavity? Well, that, my friends, is a local max. So we get 0 is a local max. I don't have a less space, so I'll just write it over here, local max. And that's because the second derivative was negative. So we know that it's got to be concave down. So we know it's a local max. All right, square root 48, plug that in. What do I get? I get 3 times square root 48 squared, which thankfully just simplifies, minus 48. So 3 times negative square root 48 is 3 times square root 48, minus 48 is 2 times square root 48. So this is 2 times 48. It's like 96 or something. It's greater than 0. I don't really care what the number is. I just want to know whether it's positive or negative or 0. When I put in square root 48, it's positive. That means it's concave up. So that's got to be a local min. And lastly, I'm going to be plugging in negative square root 48 into my equation. But because of the square, it's going to be the same result because it's squaring off the negative. So this is still going to be greater than 0. So we get another local min. Right? Greater than 0, concave up, local min. All right, so we've classified all our critical points. There are local max, local min, and local inflection, and local min, local max, local min. Yeah, okay. I said it right. We need to find possible additional inflection points. Additional inflection points. How do we find additional inflection points? That's when the second derivative is equal to 0 or when the second derivative is undefined. So d squared y dx squared is equal to 0 or undefined is how we find additional inflection points. So we know our second derivative. It's right over here. So we'll take our second derivative. It's never undefined because it's just a polynomial. It's an x squared. So it's never undefined. So we don't have to worry about this one, thankfully. We just can focus on the second derivative equaling 0. It's just make sure people know I'm not just saying it's never undefined. It's a parabola. 3x squared minus 48. Every x I plug in, I can get a y value. There's no division by ear, 0 errors. There's no log errors. There's nothing there except just a normal polynomial. So it's never going to be undefined. Let's take the second derivative equaling 0. The second derivative we know is 3x squared minus 48. Set it equal to 0 and solve for x. We get x equals plus or minus 3. We square both sides, and we do the absolute value plus or minus thingy thing, and you get x equals 4 and x equals negative 4. Are those listed before? They are not. These are new. Before we had 0, square root 48, negative square root 48. Here we have new things. They're not local mins or local maxes because I would have found them. These are all the local mins, local maxes. If x equals 4 was a local min or local max, I would have found it using a critical point. So it's not that. So what else could it be? It's got to be an inflection point. So these guys right here are inflection points. All right, so we have a function where we have two local minimums and one local maximum, and we have 2 inflection points. So finding the local max, yes, we did. Finding the local min, yes, we did. Finding inflection points, yes, we did. All right, so we have all those. And now we want to find the absolute max and absolute minimum. Well, we're almost home free with absolute max, absolute min, because absolute max, absolute min occur at one of the critical points. These are the critical points right here, or at one of the endpoints. And these are the endpoints right over here. So we got to list all the critical points, list all the endpoints, and if we have an absolute min or absolute max, it's got to be at one of those places. All right, so let me just make some space over here, and I'll make a little table. 0, square root 48, negative square root 48, and my endpoints are negative 10 and positive 10, because they told me those are the endpoints. So those are the 5 possible places for absolute max, absolute min. And how do I determine the absolute max, absolute min? Well, it just means the biggest or the smallest possible y value. So I got to find y values. So I'm going to put the y value here, and I'm going to use that to figure out the biggest or smallest y value. So here's the equation I'm going to be using. Of course, it's already in Desmos, and I'll make a table there and plug in all these values. Okay, move me over there a little bit. All right, so let's get rid of this guy, and let's find the one we were just doing right here, this one here. X to the 4th over 4 minus 24x squared plus 20 is this W shaping thing. And I'm going to make a little table out of it. And I got to remember all my values. I think we had 0, negative square root of, SQRT, negative square root of 48, positive square root 48, and we had 10, and we had negative 10. They're not in the right order that I put them on the lecture notes, but I can't remember everything. So 0, square root 48, negative square root 48, negative 10, and 10. Again, the order is a little bit wonky, but it doesn't really matter. We just have to look for the biggest y value, and the biggest y value is 120. So 120 is the absolute maximum y value, and negative 556 is the absolute minimum y value. Just because they occur twice doesn't mean anything. We're just looking for the biggest possible y value and the smallest possible y value. And if you want, you can restrict the domain of this thing. I'll remind you how to do it. You make a bracket, you put in the endpoints, and then you can tell Desmos to not graph the whole thing, just graph the valid numbers based on the endpoint. So this is the negative 10 to 10 region. Here is an endpoint where we had a maximum of 120. And here is this local minimum where we had a minimum value of negative 556. Okay. I'm just going to write down here y equals 120 is absolute max. And y equals, I think it's negative 556 was the absolute minimum based on the numbers that you'll have to write here. I'm a little lazy. Also, I don't want to spend so much time writing stuff down. But negative 556 would be the local minimum, and 120. Yeah, I got it right down. All right, so there's hopefully a nice little review also of finding local max, local min, inflection points, and absolute max and absolute min. All right, well, I got some more examples of those things. And for these ones, I'm going to, once again, invite you to try them. And I'm not going to do them step by step. I'm going to invite you to work on it. And then I will show you my completed solution and go over the steps afterwards. Instead of in real time, I'll just review them. And then hopefully you can compare them to your approach as well. So I'll see you in a few minutes after I finish writing out my solution to this example B right here, D right here. And hopefully you will also have tried it in the meantime. Okay, so if you gave that a try, welcome back. If not, you're still here, so welcome here. I'm going to go ahead and find the local max, local min, inflection points, absolute max, absolute min for this example, ln of 1 plus x squared. So I'm going to find the derivative. That's a key feature for a lot of this stuff. I'm going to be using the chain rule. So I got the derivative using the chain rule. That's this one right here. I'm going to find out when the derivative is equal to 0 and when the derivative is undefined. That's my critical points. I solved this algebraically for when the derivative is equal to 0, and I found out that x equals 0 is the only value of x that makes the derivative equal to 0. So there's one critical point at x equals 0. For the derivative being undefined, we do have a division, so it is possible to divide by 0. We divide by 0 when the bottom part is equal to 0. So when 1 plus x squared is equal to 0 is when I would be dividing by 0. As it turns out, 1 plus x squared equals 0 has no solutions. It would only be possible if x squared is negative 1, which doesn't work with real numbers. So there's no place it's undefined. Even though there's division, we never divide by 0. So there's no additional critical points from the derivative being undefined. So one critical point to classify as a local min, local max, or inflection point. I'm going to use the second derivative test. So the first thing I'm going to do is find the second derivative. So here's my first derivative. I rewrote it up here. To find the second derivative, I have a function on the top, a function on the bottom. I use the quotient rule. So derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. And that gives me this messy stuff, which I simplified down to be 2 minus 2x squared over 1 plus x squared all squared. Second derivative test says I take the critical points, plug it into the second derivative test, hope I get a positive number or a negative number, and that tells me whether we get a local max, local min. So I took 0, I plugged it into the second derivative formula, and it worked out to be 2. And since 2 is greater than 0, we know it's concave up, and that means that x equals 0 is a local minimum value. So I have a critical point and its local min. There are no local maxes because I would have found them from critical points. To find any additional inflection points, because there could be more inflection points than the ones that I didn't find from the first derivative, I'm going to use the second derivative. So I take the second derivative, which we already found, and I set that equal to 0, and I take the second derivative and find out what's undefined. So that's how I find my additional inflection points. Okay, so second derivative equaling 0, I use my algebra to solve this equation here. I did a bunch of like simplifying, and I got x squared is equal to 1, which give me 2 inflection points. 1 and negative 1 are 2 inflection points. There are 2 inflection points. Neither of them were a local min or local max. X equals 0 was the only local min or max. It was a min. So these are definitely inflection points because they can't be anything else. What about when the second derivative is undefined? Well, the second derivative is undefined when we get an undefined calculation, like when we divide by 0. So we would divide by 0 here if the bottom part was equal to 0. So only if the bottom part is equal to 0 would we have a division by 0 error. So I used some algebra to solve this one, squared both sides. And it turns out that it's also not possible. So it's not possible for the second derivative to be undefined, so no inflection points from there. But we did locate 2 inflection points using the second derivative at x equals 1 and x equals negative 1. Lastly, we were asked to find the absolute max, absolute min. We've done most of the work already. Absolute max, absolute min occur either at a critical point, there's only one of them, x equals 0, or at an endpoint, and we were given endpoints at the very start of -3 and +3. Let me circle that properly. So I'm going to make a list of my critical points or critical point and my endpoints. So that is over here. If I can slide this. To find the absolute max, absolute min, I just list the critical points and the endpoints, and I find the y value. So for each of these y values, I just plugged in the x number into the original formula. We're looking for y values. We're not looking for derivative values. We're not looking for second derivative values. Absolute max, absolute min is a y value. So you plug it into the y equation. I plug in 0 and I get a y value of 1. Oops, that's not a y value of 1. I plug in 0, I get a y value of 0. It's ln of 1. ln 1 is 0. I plug in -3. I got about 2.30. It's ln of 10. And I got the same value when I plugged in +3. The largest possible y value is called the absolute max. That's the ln10 number, or about 2.30. And the lowest possible y value is 0. So that's the absolute minimum. So y equals 0 is the absolute minimum. Y equals ln10 is the absolute maximum. We can verify that using a picture. Here's the function, y equals 1 plus x squared. I restricted it from -3 to +3, just so visually it's a little easier to see. You can see that the very lowest the graph goes is right here, which is at y value of 0, x equals 0, y equals 0. And there's two locations where the function achieves its absolute maximum. Its absolute maximum is 2.303. Approximately, it's exactly ln10. And it occurs twice. It occurs when x equals 3 and x equals -3. But the answer to the absolute max is the y value of ln10, approximately 2.303. All right, so that's the solution that I wrote out for this example. How'd you do? Did you remember all the steps? Did you get the critical points? Did you remember to find the derivative and second derivative undefined? Did you write out the list for the absolute mix, absolute max, absolute min? Did you classify using like not the second derivative test? You could just do increasing, decreasing to classify your critical point, or you can use the second derivative test. It oftentimes works. So how'd you do? How'd you do? How'd you do? Yeah, I know you can't answer me, but anyway, hopefully you did okay, or hopefully my solution helped uncover exactly where you might have gotten stuck and how to fix that. And that, my friends, is how you do absolute max, absolute min, as well as local min, local max, inflection points, all that kind of stuff like that. Don't forget, you'll also done intercepts. Intercepts is when x equals 0, y equals 0. We've also done asymptotes. Asymptotes are limit when x approaches infinity, or when y goes to infinity. So we've done intercepts and asymptotes. Don't forget about those good things. I haven't reviewed them here because we've done them many times before, but certainly reach out if you want to see more practice on those. All right, well, I do have more practice problems. I think for these kinds of problems where you're finding all the local and absolutes and critical points and inflection points and stuff like that, just practicing on different types of problems is helpful. So I have E, F, and G here. I'm going to invite you to try these. I'll just write out my solutions, and I'll just show the screen of my worked out solutions so you can double check your answers. But I'm not going to go through all the steps like I did in the previous one. But if you do want me to clarify anything, please do reach out. I'm happy to go through any of these examples and show you the steps. Hopefully I don't make any errors, so you don't have to correct me. But I'll be careful. I'll check all my steps to make sure I minimize any possibility of making an error. And hopefully you found this video very helpful. I do want to remind you that at the end of this section of the lecture notes, I do have all of the vocabulary on one page, all the local min max, absolute max min, increasing, decreasing, all the different vocabulary words that we've done. It can be kind of confusing if you're going through this for the first time. And so this is just kind of all in one page, so it's easier to sort of remember what's going on. And then I have some summary of important facts. Critical points are always going to be local min, local max, or inflection points. To find a local min or max, you need to find the critical numbers, critical points. To find an inflection point, you need to find the critical points and also these additional second derivative points where they're 0 or undefined. Absolute max, absolute min always happen at a critical point or an endpoint. Not all functions have an absolute max, absolute min, so be aware that you don't have to have an answer. You just say it doesn't have one. And there's other important things that I mentioned also about intercepts and asymptotes and undefined points, things like that. Okay, so I'm going to leave you now to try E, F, and G. I'll write out my solutions, and in a few moments, I'll pop back in with the worked out solutions for you to check, and then invite you to reach out to me if you have any questions. Hopefully all this was useful and helpful, and that you have an enjoyable day, and that you do indeed let me know if there's anything I can help you with. Okay, well, here are the solutions for the first two additional practice problems, E and F. And my computer stopped working, so hopefully this video still records. And I will show you the answer to G after I restart my computer and hopefully stitch this together a little bit. Okay, thanks.